The organizers asked Uli Scholbeck and me to talk about the question of whether the Hubbard model is superconducting or not. And so I think that's what we're going to do. Uli is going to talk about the zero temperature perspective. I'm going to talk about what happens as we cool down from high temperatures. And specifically, I'll talk about what happens in cluster dynamic mean field theory and quantum Monte Carlo approaches. So yes, this is the basic question I'm going to look at in the first part of my talk. And then I'm going to move on and make some contact with the previous session on the pseudogap and ask the question, how does a system become superconducting in the presence of a pseudogap? Okay, so we've heard about the Hubbard model, which is believed to be a good description of the group rates. There's a single band crossing the Fermi energy that's described by this Hubbard Hamiltonian. Specifically, we're going to be looking at a Hubbard model that has both a nearest neighbor hopping T and also a next nearest neighbor hopping T prime, and of course the Coulomb-Repagin U. It's got all the basic physics that's needed to describe these systems, and again, the question I'm going to look at now is, does this model have a superconducting state? So here is the situation a long time ago, before we had cluster dynamic mean field theory. These are results from determinantal quantum Monte Carlo on a 4x4 Hubbard lattice with a Coulomb-Repagin of 4T. And this model is doped. What's shown here is the filling dependence from 0.5 to 1 of the D-wave pair-field susceptibility at two different temperatures. And if you can't really see much here, it's because there isn't really much there. It's hard to see anything. You can see some enhancements. So for example, these solid symbols are the fully renormalized D-wave susceptibility. The open symbols are just the BS susceptibility. So at least you can see some enhancement, those two have filling due to the interactions. So that's pretty much the only conclusion you can draw from this. A few years later, it was possible to go to larger systems. So this is an 8x8 Hubbard lattice, again, determinant of quantum Monte Carlo. Same Coulomb-Repagin. This is the temperature dependence now of the D-wave pair-field susceptibility. And we are sitting at a filling of 0.87. And so what you want to look at are these solid symbols. That's the, again, fully renormalized D-wave pair-field susceptibility as a function of temperature. It does go up. There's again some enhancement over the BS susceptibility. These lines are from diagrammatic calculation. So the problem is you can't really go to lower temperatures because of the fermion sign problem. So this was really the state of the art until about 1993. There was certainly no conclusive statement to be made about whether this model becomes superconducting or not. Around the same time, there was, of course, the invention of dynamic mean field theory by various people, including some of the organizers. And this you can view as really the opposite limit to these finite size approximations. Here, you're treating a system in the thermodynamic limit, but you're only treating the local correlations of the system. Now, then there was a big push in the years after that to develop cluster extensions. This was not an easy task, so it took a while. But the first ones came out in '98. So this is came out from Mark Cherrow's group. Matthias Hettler and others developed the dynamic cluster approximation. Lichtenstein and Knopf-Nielsen also had their own cluster dynamic mean field theory, and then Bobby Cochlear, Chair, and others had a real space theory context. So this you can view as something, an approximation that really sits in between these two, right? It was really developed as an extension of dynamic mean field theory in order to include non-local correlations in addition to the local correlations. But you can also come from this side, right? You can view it as this is a finite size cluster, but it has some boundary conditions on it that allow you to describe the thermodynamic limit. Okay, so here is a bit more detail on one of these cluster extensions. That's the one we've been using, the dynamic cluster approximation. We've heard about it in the previous talk. So in this case, you have a momentum. You define a cluster in momentum space. The way you do this is you take the first filament zone, coarse grain it. So the assumption is that the self-energy is only weakly momentum dependent. It is well described on a coarse grid of K points. That allows you to map the infinite size lattice onto a finite size cluster embedded in the field. And then you can solve that using numerically exact methods. Is it good?
Yeah, the share was paused for some reason.
Oh, okay.
You're good to go.
Perfect. Thanks. And so you can solve this problem then, and the state of the art there is again quantum Monte Carlo. Okay, so shortly after these quantum cluster methods have been developed, then people looked at the 2D Hubbard model, the doped 2D Hubbard model, specifically looking at the question of superconductivity. These two papers came out in 2000, shortly after one another. This one was first. This was our calculation. This is a calculation of the doped Hubbard model. I think the Coulomb margin here was rather high. I think 12 times the hopping T. And this was actually a calculation done not with quantum Monte Carlo, but with the non-crossing approximation. In expert circles, that's also the never correct approximation. But nevertheless, it gave a very nice superconducting phase diagram here. It had a dome-like structure. We couldn't go to the lower temperatures because of problems with this approximation. Here was a calculation by Sasha Lichtenstein and Katznaison, also looking at, just like in this case, at a 2x2 cluster. That's really the smallest cluster you can look at to get D-wave superconductivity, calculating the magnetic order parameter here and the superconducting order parameter. And again, you find this dome-like structure. Shortly after that, we then also did a calculation using Hirsch-Phi quantum Monte Carlo to solve the cluster problem. This is the phase diagram that came out of this. It now also had a pseudo gap, and we've heard quite a bit about that in the previous talk. Here is the D-wave superconductivity. And again, this was a 2x2 cluster calculation. The big question then, of course, was, what happens if you make this cluster larger? And so in 2005, we were able to do that. We were able, at least for a Coulomb margin of 4 in units of the hopping T and the doping of and the filling of 0.9, we were able to go to 26 sites and calculate the Fairfield susceptibility. This, what's shown here is the inverse Fairfield susceptibility. And again, you see that even in the largest clusters, it goes through 0, so meaning you get a superconducting state at a finite temperature. Okay, so then there's lots of other groups who did similar calculation. Here I'm showing some of these, and I apologize to anyone who is not represented here. Here is work by Christian Howley and Gabi Kotlia. This is, I believe, a 2x2 cluster also. Some of this actually, I think, was also done with NCA. Some of this was done with continuous time quantum Monte Carlo. So again, you see the dome here. So here is a calculation by Salma Kanchala, Andre Marie, Gabi Kotlia, and collaborators, calculating in the ordered phases, again, the magnetic order parameter and the D-wave superconducting order parameter. Again, you see a beautiful dome-like structure here at finite doping. This is more recent work by Emmanuel Gull and Andy Millis, Olivier Parcollet. It's very beautiful work looking at the superconducting phase, mapping out the phase diagram as a function of doping, X, and Coulomb margin. So if you sit here, you see that you have a pseudo gap here, a superconducting phase, and a normal state. So there's quite a bit of evidence at the time from cluster dynamic mean field theory that the Hubbard model is indeed superconducting. We went one step further in 2014. We modified the DCA algorithm a little bit by introducing a continuous set energy, a set energy that has continuous momentum dependence. This allowed us to go to even larger clusters. So here again is shown TC as a function of cluster size. This is again for a Coulomb equation of 4. And you can see there is something that looks like convergence for the very large clusters. Here we could go up to 56 sites. With a little bit of imagination, you can even put a scaling curve through here that's given by this Kossler-Stauler scaling behavior. And from that, then you get a TC of 0.02. We did this also for a larger U. So here again shown is what I just showed you for a U of 4. But then we went to a U of 7. And as you can see, TC goes up. TC in this case was about 0.05 T. And again, this certainly there is no indication that for the larger clusters, TC significantly goes down. So there's really no reason to believe that in these cluster methods, in the limit as they become exact, there is no superconductivity. This really looks like superconductivity is there in the exact large cluster limit. You can also go to even larger U's, and you find that a U of order the bandwidth is in fact optimal. This is where you get the highest TC. So this is the situation regarding superconductivity from cluster dynamic mean field theory. Now, of course, I do have to mention stripes. I'm sure we will hear a lot about that in the next talk. So the question, of course, comes up, what about magnetic and charge stripes? So there's a large body of work at 0 temperature from BMRG and related techniques that at least at 1/8 doping and for a T prime that's 0, clearly find evidence of a striped magnetic in the striped charge state. Now, this is not BMRG. This is something that comes out of Tom's group, and it's really beautiful work by Edwin that was done, I think, 2 years ago, looking at this problem using the determinantal quantum Monte Carlo, so coming from high temperatures. And so they looked at this 16 by 4 site cluster and calculated. What's shown here is essentially SI dot SJ, but there is a phase factor on the B sublattice. So if everything is a plus here, it really means antiferromagnetic correlations. And so what's shown then here is that if you cool it down to low enough temperatures and sit at a finite doping, for example, here at 1/8 doping, you again get beautiful stripes. These are magnetic stripes. And this was really, I have to say, a very heroic calculation. I think the average sign was less than 1% in these calculations. Edwin can tell you. So you really have to get extremely good statistics to get this. So I was interested in this and did a very similar calculation. So in our DCA code, we can, of course, simply switch off the mean field. And when we do that, we also have just a finite size cluster, which is then solved with a quantum Monte Carlo solver. Now, for most people, you can just view this as exactly the same thing as this. For the experts, there's some differences. This is continuous in time. This uses a discretization in time, but that's just details. Nevertheless, if you do this calculation, you find the same thing. You find a beautiful strike state in the magnetic correlations. Then, of course, the question is, well, what happens now if I switch on the mean field? Okay, so if you do that, the stripe is gone. So clearly, cluster dynamic mean field theory, or specifically dynamic cluster approximation in this case, frustrates stripe formation and favors superconductivity. So this is, I think, still an unsolved problem. So what's shown here, these are antiferromagnetic correlations, and these are all plus. So that means there is no high phase shift. I should have explained this a little bit better here. What you see here is a pi phase shift with the domain wall in the anti-ferromagnetic corollary. So that's not seen in the DCA calculation. If you switch the mean field off, it's there. So we got both the stripe and the effect. So this is only it's only a stripe in the magnetic structure, not a stripe in the charge. At these temperatures, there's nothing in the charge. There's nothing in the charge. It's only magnetic. But then, what do you mean by mean field? Which mean field? So mean field. It's just a DCA. Dynamic. Yeah, it's just DCA. But what I mean by that is, if I switch off the mean field, right, then I just have a finite size cluster with periodic boundary conditions. So again, I think that's an open question that needs to be solved. Where are the stripes in cluster dynamic mean field theory? Okay, so I can solve it right now. So I'm going to look at a different question. So before I get to the pseudo gap, and I have to watch my time. I just want to say a few words about, so we find this superconducting transition in the Hubbard model using these methods. Then, of course, we can ask the question, what's the mechanism for that? And we are really ahead of experiment there because we can calculate the interaction. We can calculate the pairing interaction. Experiments cannot do that, but we can do it in the computation. You can look at the beta-side-beta equation then, which relates the gap function to the pairing interaction. You can think of this essentially as an exact version of the BCS gap equation. This is also related, of course, to the Debye pair field susceptibility that I've shown you before. Essentially, for this particular problem, the pair field susceptibility goes like 1 over 1 minus the leading eigenvalue of this beta-side-beta equation. So when this thing goes through 1, you have a transition to your superconductor. You can also look at simplified approximation. You can make it separable, where you look at the pairing interaction separate from the pair propagator here. What you would have in BCS theory is that you have an interaction that's more or less constant. It's set at very high temperatures. It's then constant. And the superconducting instability arises from the Cooper log divergence in the pair propagator. Okay, so now, as I said, we can calculate the interaction. You can also write it in this form as a sum of 3 different pieces. You can resum these in terms of charge and spin degrees of freedom, and then look at what is responsible for the structure in the pairing interaction. And what's shown here is this pairing interaction as a function of momentum transfer. And you see that it's all coming from the spin. So in a sense, it's very similar to what we heard before in the previous talk. It's a diagnostic of which correlation is responsible for the structure in the pairing correlation. And you see clearly it's the spin degree of freedom. So this is looking at the momentum dependence. You can also look at the frequency dependence. Shown here is the frequency dependence, not of the pairing interaction itself, but of the leading eigen function, and you can compare that to the frequency dependence of the spin susceptibility. Very similar frequency dependence. There's also beautiful work that came out in 2009 from André Marie and David Seneschal, looking at this as a function of real frequencies. And you can see that this is essentially the gap function. The structure and the gap function, you can relate this to structure in your spin susceptibility. So there's a lot more work on that, which I won't go through, but from all this large body of work, you can conclude that in the Hubbard model, the pairing interaction that leads to superconductivity comes from the spin degree of freedom. It increases with momentum transfer, and the dynamics reflects the spin fluctuation spectrum. Okay. So now, with that, I'm going to ask the question, okay, in the pseudo-gap region, how do you get superconductivity? And so here it's just showing that we do have a pseudo gap in these type of calculations. So here is a typical phase diagram that you get in a DCA calculation for a 12-side cluster. Pseudo gap here and superconductivity here. The pseudo gap is defined as the maximum in the bulk magnetic susceptibility. This is where the pseudo gap temperature is. And so now you can ask the question, how does superconductivity arise in the pseudo gap region? And this is again another slide just to show that there's many calculations, and we've heard about it before, that show that the Hubbard model does have a pseudo gap. I won't have time to go through this. Instead, the question I'm going to ask is again, what happens in the pseudo gap region? And so in a normal metal, as I said before, you have the Cooper log instability. This means that the pair propagator has a logarithmic temperature divergence. The interaction itself is hardly temperature dependent, but because this thing has a logarithmic divergence, any attractive interaction will give you superconductivity at some finite temperature. Okay, and it comes from the temperature dependence of the pair propagator. Now, if you have a pseudo gap, things are quite different. Parts of the Fermi-seas are actually dried out. The antinodal regions have a pseudo gap. There are no states. And now, if you calculate the temperature dependence of this pair propagator in the pseudo gap region, you see that it actually goes down. So here it is for a large doping outside of the pseudo gap region. You see this logarithmic temperature divergence. Here it is in the pseudo gap region. It actually turns down when the pseudo gap comes on. So now the question is, how do you get superconductivity when you don't have a Cooper log instability? Well, and the answer is the following. Well, you still have an eigenvalue. You still have a Kern strength that goes to 1 because I have a finite TC here. If you look at the separable approximation, if you have a pair propagator that turns down upon cooling, well, you have to have an interaction that increases in strength as you cool the system. And this is indeed what's going on if you calculate the temperature dependence of the interaction. It's very different from a BCS superconductor. It becomes very strong at low temperatures and increases as the temperature is lower. You can then also look at, okay, what if I replace my pairing interaction by a spin fluctuation approximation and calculate the eigenvalue with that? So here shown in black is the exact eigenvalue, within the limits of the DCA. In magenta is the eigenvalue from the spin fluctuation approximation. And again, you see that it describes it fairly well. You can also look at experiments. Right? You cannot calculate, you cannot get to the exact interaction in the experiment, but of course, from neutron scattering, you can get at the spin fluctuations. And so doing this involves a little bit of algebra, but this is actually, what we did here is we constructed the spin susceptibility from an RPA calculation using ARPAS data on BISCO 2212, both at 90K and also at 40K. At 40K, it's actually a little bit more complicated because we're inside the superconducting state. But what you find is, so you calculate this spare bubble from ARPAS, because ARPAS allows you to construct the G within some approximation. You then calculate an RPA form for the spin susceptibility, right? And then from that, we can calculate a D-wave interaction. And what you see, first of all, it's negative. That's because it's attractive in the D-wave channel. More importantly here is what you see is that as you go from high temperatures to low temperatures, it becomes more negative. So it becomes more attractive. This is exactly what we see in the calculations. As you cool the system, the interaction becomes strong. Okay. 1 minute. All right. Okay, so I'm going to be real quick. So what I'm going to do in the remaining minute, I'm going to look at airfield fluctuations again in the pseudogap region here. So the question is, because we have a very small superfluid stiffness, the superfluid density is very small. Do you have phase fluctuations? Is there any evidence in the calculations that there are phase fluctuations? And so to look at this, we will look at, instead of the airfield susceptibility, this is of course the quantity that tells you about airfield fluctuations. We're just going to look at the denominator, 1 minus the eigenvalue, and specifically at its temperature dependence. So here we are outside the pseudogap region. The temperature dependence more or less follows a log, right? You can fit it quite well with this logarithmic temperature dependence in the overdose region. Now let's go to the left in the phase diagram into the pseudogap region. And what you see is as we enter the pseudogap region, the temperature dependence changes quite a bit to this one, right? You see an extended region that has linear temperature dependence, which then merges into a region down here that has very much positive stylistic. So what I'm going to tell you now is that what this is reminiscent of, this linear region, are phase fluctuations, because so here's the plot again, fitted by a linear temperature dependence. You can calculate this also in the classic XY model. So that is a model that only has phase fluctuation. It only has a phase degree of freedom. It does not have an amplitude degree of freedom. The amplitude is already fixed. And the temperature dependence there is very similar, right? A very extended linear region merging into this Kosterlitz-Saulus type behavior. And I don't have time to go through this, but you can look at the local pair field at a given site. You see in the pseudogap region that it actually saturates. And so you're left with phase fluctuation. And the way superconductivity emerges in this region then is by increasing the phase coherence. This is not something purely theoretical. One can actually measure this. So in the spirit of this conference computation, these experiments, this was actually worked out a long time ago by Dr. Flatiron. You can measure this in a tunnel junction between two superconductors. This looks like a Josephson junction, but it's in fact not, because this is something that's operated at a temperature that sits right in between the TC of this superconductor and the TC of this superconductor. So you need to have two different superconductors, and then you can work it out, and you find that the tunneling, you have an excess tunneling current, which is actually proportional to the airfield susceptibility. And if you go through all the algebra, you can show that from that you can actually then calculate the temperature dependence of these airfield fluctuations. This works beautifully for BCS superconductors. It's been tried for the cuprates. It's much harder to do there. I would say the results so far are inconclusive. So maybe there's more work to be done. And I'll just leave you with this. Thank you.
Yeah, so to elaborate on the very last slide of your talk, not this one. So I'm aware of an experiment by Jean Bessoir and co-authors that did exactly this thing, motivated by this paper, actually. Okay. And at least, so they do that between the superconducting optimally doped NTCO and underdoped NTCO in the pseudogap regime. Right. So that's exactly that. Yeah. And my recollection is that they do claim from the experiment that the range of temperature above TC where there is phase fluctuation is superconducting fluctuation is only 20 Kelvin.
That's right.
So can you elaborate on the?
So I'm not. Yeah. So I'm not an experimentalist. So what I'm told is that it's a very hard experiment.
Yeah, everybody saying this, including the authors.
So because first of all, you have to find the right materials, right? You have to have one with a very high PC, one with a low PC. There's also the issue of separating this excess current that's due to the pairs tunneling from the quasi-particle current. So that, I think, is an issue as well there. And also, I don't think that paper actually, I didn't have time to go through this, but I don't think it performed this analysis where you would take the IDV curve and actually integrate it over the voltage, because that would allow you to really look at the temperature.
You can set the impedance of the junction.
Right. Yeah. So and so this, if you do that, I think you rely on this Ginsburg-Landau type form, this one here, of the Peter fluctuation. If you did this, you wouldn't rely on this. This is an approximation. So, yeah.
You go back to when you compare the eigenvalue of the PCA with the RCA. Yeah. Mm-hmm. So was the U the same in the two calculations? U bar.
You mean in the two?
I mean, the exact eigenvalue.
Well, so there is no U bar in the exact, right?
That's right. But there's a bare U.
Yeah, so U bar,
Not a bare U.
U bar is usually you have to take something much smaller. Right? So there's kind of more screening. Which,
So there's one adjustable parameter.
It's an adjustable parameter here, but then you look at the temperature.
And also you were able to make it consistent with the other one.
So here, U bar, I believe we took from the Arthas data. You can look at the Fermi velocity along the nodal direction, and you can, let's say you use a spin fluctuation approximation for the self energy that gives you a real part that gives you that dispersion, and then you can fit the U bar.
Okay. So I think we should probably move to the next talk. I will let less than the speaker.